Hi, welcome back. So part two, the fundamental theorem of line integrals. In this example, example number two, we want to evaluate the work done. Now notice they say that the gradient of f. Well, remember, if this is the gradient, we already know it's going to be conservative because remember, to get the vector field from a function, we have to know the gradient of the function anyways, and they have to be the same. So that's our gradient right there. So we're still trying to find work. But now notice they gave us the function itself. They didn't give us the vector field, but they gave us they gave us that potential function. And it says any path. Well, since this is the function, that's what this kind of saying right here. That because they gave us the gradient, this is automatically we can assume that this is conservative. So because they gave the function, we can assume this is going to be conservative. So this is pretty easy to get the work done here. We can just take that function that they gave us, this cosine pi x plus sine pi y minus xyz, and evaluate. And we can evaluate that from 1.5 to, and we're going to end at this 2, 1, negative 1. And we just plug that in. So this is going to become the cosine of 2 pi, which is just 1 plus the sine of pi, which is 0, minus this is going to become oops, sorry, pen stuck. Uh, 2 times 1 times a negative 2 minus plug in the 1. Cosine of pi is 1. Oops, sorry, negative 1 plus sine of pi over 2 is 1, and then minus, this is just going to be 1 times 0.5 times 2, and whatever that's going to be for us right there. And there's your work done right there. That was pretty easy. So some simple vocabulary, very important. To use the fundamental theorem, we have to have a vector have a vector field that is conservative. And remember, what that's telling us is that the vector field equals the gradient. We just saw that above. If that is true, we can find what is called the potential function, and then just use the FTC from last year. If a vector field is conservative, then we can if a vector field is conservative, we are saying that it is what's called path independent. Therefore, it doesn't matter how we find the integral, solve that line integral, they're going to be the same. A path is considered closed like a circle. If we start and end at the same place, we're going to talk about that. That becomes very important when we talk about something called Green's theorem. A path is simple if it doesn't cross itself. Like something simple is a circle. That's simple. Something not simple is like a figure eight. This is not simple. We'll talk about how to solve paths where they're not simple like that later on. Open is just basically anything contained inside the region. It's connected is if we are just, like I said, we're connecting 2 points. All right. And what makes these really nice is that they're what we call simply connected. No holes, no gaps, nothing. It's just a nice straight path. We're starting at A and going to B. Nice simple path. All right, so let's take a look at an example of a line integral, a work problem right here. So let's say we have the following work problem. We are going from 1, 1, 0 to 0, 2, 3, and they give us this path right here. Notice they're not telling if it's, so they're not giving us really the path. So this is going to be conservative because they didn't really give us a path much for it. So we're going to try to evaluate this integral using parametrics. One way I could do it, we're going to try this the parametric way, which is not the nicest way. We're going to find out. So to start here, I can say x, we're starting at 1. We're going to 0, so I would go minus, what's that, minus 1t. Y starts at 1, goes to 2, so I can say that starts at 1 plus 1t. And z starts at 0 plus 3t. And if I want to solve this using parametrics, ready, you're going to find out really quickly. Remember the rule here is to solve our integral, it's going to be the vector field as a parametric dotted with the path, the derivative of the path, and that's going to become dt. So we are going to need the path, the derivative. X prime is negative t, y prime is just t, z prime is just 3. Whoops, sorry, that's just not correct. 1, 1, 3. There we go. All right, so we do have to convert our parametric here. Let's go ahead and do that. We do have to convert our vector field. Let's see here. There it is. We do have to convert our vector field into a parametric. So the first one is just going to become 2x. Well, remember what x is. That's just 1 minus t times y, which is just 1 plus t times z, which is 3t. X squared, which is just 1 minus t squared, plus z, which is 3t squared, and then 2 times y, which is just 1 plus t times z, 3t. And we're going to dot that with this negative 1, 1, 3. Now, right away, I can say, yeah, this is going to be pretty ugly to solve. This is not nice to solve. So there must be an easier way. So let's see if it's conservative. Let's just check if our vector field is conservative. So let's see. To be conservative, because this is in 3D, if this is conservative, because it's 3D, we have to look at the curl of the vector. And to get the curl, you might remember it is going to be this ijk. It's the partial with respect to x, the partial with respect to y, the partial with respect to z, and with respect to z, and that's going to become m n p. And this is our m n p right there. So our rule, if you forgot the rule, I'm going to go ahead and generate it for us. If I block out the first two, that's going to be the partial of p with respect to y minus the partial of n with respect to z. So it is going to be the partial of p with respect to y minus the partial of n with respect to z. And blocking out the next two, that's the partial of p with respect to x minus the partial of n with respect to p. So that's going to become the partial of p with respect to x minus the partial of m with respect to z. And then lastly, it's the partial of n with respect to x minus the partial of m with respect to y. So it'll be the partial of n with respect to x minus the partial of m with respect to y. All right, so let's check. And to be conservative, they all have to be 0. So let's go ahead and plug this in. So for the first one, the partial of p with respect to y is just 2z. The partial of n with respect to z, 2z. So far, so good. I'm liking it. The partial of p with respect to x, well, there's nothing there. The partial of m with respect to z, 0. So far, so good. So far, we're good now. Partial of n with respect to x, that's 2x. The partial of m with respect to 2y, with respect to y, excuse me, minus 2x. And notice this is 0, so this is saying this is conservative. And because it's conservative, we can use our potential function now. Whew, path doesn't matter. So let's see here. So to solve this now, looking at the x's, now we've got to find our potential function. Looking at the x's, this is going to become 2xy dx, which is just x squared y. Looking at with respect to y's, that's going to be this x squared plus z squared dy, and that's going to become x squared y plus z squared y. And with the z's, that's this 2yx dz. Whoop, that's a z right there. And that's going to become y squared. Oops, sorry, not y squared, it's y z squared right there. That's just it, y squared z. They all have their constants, but so our potential function, remember, look what they have in common. Here you have this x squared y, x squared y. So my potential function is going to be this x squared y. What do they have not in common? These two have this yz squared, so plus this yz squared. And there's my potential function. I'm going to use my FTC. I'm starting at the point 1, 1, 0. And I'm ending at 0, 2, 3. Plugging in everything, plug in the 0, we get 0 plus, what's that, 2 times 9, minus, plug in the 1 here, that's just going to become 1 times 1 plus 0. Oh, that's nice. That just becomes, with 18, we get 17. And there's your answer right there. So because this is a conservative vector field, I don't have to solve this ugly work equation. I can just use my potential function. Remember, this right here is my potential function in order to solve our work problem. All right, hope you enjoyed the video. I'll see y'all later.